Okay, good morning, everybody. Nice to see many people joining us here for the fourth AutoCFD workshop. And in the next couple of minutes, I would like to give you a quick run through test case 2, talking a little bit about the test case. We'll keep that very, very short. I'm pretty sure you know the test case. Do a little bit of a recap of AutoCFD4. I know there have been many questions about test data and the dependency of test data on wind tunnels. So I'll talk a little bit about this topic. I cannot go into the details because there wouldn't be enough time, because I certainly would like to talk at high level a little bit about the outcome of the data I've seen coming with AutoCFD4. Perhaps we'll see later on in the next days. I know people are very interested in this question. Should we include wind tunnels in simulations? There's more stuff I've prepared, which I can share. Won't fit into the slot here right now, but perhaps something we can cover in the next days. So in terms of test case, you see just eye charts. I will really not go into the detail. I trust that everybody knows the DrivAer model. It has not changed to all the previous AutoCFD workshops, so there's nothing new about it. We'll still look at the two variants, so the baseline variant, but also the test case to be with the front wheel deflectors. Most of the participants actually analyzed both. That's good. Some which did some specific study like noise factor focused just on one, which is, I think, fine. In terms of test data, again, nothing new here. You know, we have the aero forces, but we also have the surface pressure. We have velocity profiles, and we have flow field data. So that's all unchanged. And I also, like in previous workshops, you all provided the information via the spreadsheets. And as I promised, in return, you get all the spreadsheets with the test data being included, with all the comparisons being included. The only thing I have to say, that will only happen over time. So I still expect that I managed to do this like perhaps until end of November, but it won't happen within the next days. There's almost 80 submissions, and I have to go through all of this stuff, and there's manual work to do, so it will take a little while. But you're going to get the data. In the meantime, I can mention this already, all this data and the cross-plotting is all available via Astrid's dashboard. I think the link will be shared so that you can start looking at the data pretty much immediately via the dashboard. Okay, a little bit of recap regarding what we found in AutoCFD4. And I think the first point to me is important. I need to emphasize this again also for AutoCFD4, is that we used in AutoCFD4 first time mean calc to analyze the statistical relevance of the data. And we found that not all the data has been properly stabilized and have been run long enough. And that's what we saw again. I'll show some data later on. I think that's something we need to keep in mind, specifically when we talk about stuff like noise factors. When we already have some concerns that the runs are not long enough or the averaging window is not long enough, then that creates questions. Overall, I think we have not seen that in AutoCFD4 things have improved too much versus AutoCFD2. And I think that story continues, as you will see in a minute. And we also have seen that there was a lot of variability in the results we got. And I'll show some stuff in a minute. We also, when we then looked at the impact of the front wheel deflector, only a fraction of the submitted data sets achieved the quality criteria which we defined, like 2.5 counts for the prediction of the impact of the front wheel deflector on drag, and 5 counts in terms of the impact on lift, front and rear lift. There was, to also say something positive, and there is certainly a lot of positive, so I don't want to be negative here. There are definitely a number of submitted data sets which are really good, which are really close to test and show really good performance, and that's important to recognize here. These are just a few pictures. Again, I've not the time to go into details. On the upper left, you see plots from AutoCFD2 and AutoCFD4 regarding the spread in predicted drag values, and you see the red bar, which is kind of the acceptance range from the testing perspective. You see obviously big spread and also, let's say, mostly over predicting the drag. If you look at the upper body pressure, you specifically see that at the rear window, there's a lot of variability in the results. That was in AutoCFD2, and that's still what we have in AutoCFD3. We also had some systematic findings, like on the body, on the bottom here, we see comparison of steady state and transient results, velocity profiles underneath the vehicle. So I think the coloring red for transient, blue for steady state clearly shows the difference. And I think the conclusion last time was that specifically when you think about wheel wakes, that steady state analysis are not correctly predicting, for example, the wheel wake. And there's other stuff where they struggle. The same, I think, is here. We also see some comparison between steady state and transient, and we clearly see a systematic difference between the different methods. This is also recap. It shows the impact of the front wheel deflector, and as I said before, on the upper left, we see the deltas in drag, lift, front and rear. And there's some text which says there is only a fraction of the results which meet the quality requirements, which are shown in this red bands, which are plotted across the data set. So obviously a lot of variability in what has been predicted. We can also look at the delta from a pressure standpoint. We see that in some areas, like around the front wheel, the trend is kind of correctly predicted, but then there's a big spread. And certainly at the rear wheel, the trend is mostly incorrectly predicted. We can also, if we look at the results, this should animate a bit. We go back and forth. Okay, yeah, so we see there's systematic differences between steady state and transient. We see the steady state, the blue ones are far more spread out. This is all delta plots, yeah. So that's so the red seems to be more consistent, seems to be closer to test, and the same here we see a comparison between different DDS methods. So one is Palma-Damaras, the other one is K-omega SST. So K-omega SST showed a bigger spread than what we have seen with Palma-Damaras. Okay, that was a quick recap. Now let me take a few minutes because so many people were asking about these wind tunnels. Yeah, shouldn't we include a wind tunnel? And would that right away turn our results all green and wonderful? And there is some stuff I can share with you today. Actually, there's the so-called European aerodynamic data exchange community. A lot of different OEMs are participating in this. And what they did is they ran a wind tunnel correlation test last year mainly. And so a lot of vehicles got sent through different wind tunnels, including the DrivAer model. And the DrivAer model has been tested in 11 different wind tunnels throughout Europe. What I have to say, these tests were clearly focused on moving ground tests. So they tested moving ground. So they did not test what we calculate, where we do steady state. But still, I think there's a lot of stuff we can learn from this test. And all these wind tunnels are very different. Yeah, different nozzle size, different collector size, different plenum size, different bell system, different boundary layer treatment system. So a lot of reasons why their measurements could be pretty different. Yeah, and but nevertheless, they're all state-of-the-art tunnels in a sense. They all tested 140 kph and the ride heights which we have chosen. What I have to say, the model, as I said, is somewhat different to what we have in AutoCFD. We have moving ground, and because we have moving ground, we had to change the tires from the tires we are using here to a BMW tire. And we also added a mini air dam. You heard me talking about how sensitive the leading edge of the underbody is. So we tried to work around this by adding this mini air dam. And then it was open cooling. So these are the main differences. What we did afterwards, we collected all the pressure data. And what we did is we corrected the pressure data by shifting them so that at the top of the roof, they have the same value. So it's all shifted towards one value so that any differences with reference pressures are taken out of the equation. And afterwards, what I did is we created a min-max plot. The different OEMs weren't happy to share their specific test results, which is something I need to accept, and it's understandable. But we agreed that we can share these min-max plots, which shows the bandwidth of the measurements. And I'll show you some data in a minute. So what you see on the upper left is that is AutoCFD4 data, and you see I also shifted this data. You see it's flipping. Yeah, there's the original data you submitted, and then you see how at this roof center of the roof point it all collapses to one value. That's exactly what I also did with the test data. And this, what you see at the bottom, that's the bandwidth of the testing, which we got out of 11 wind tunnels. And what you see on the top is the overlay of the shifted calculation, and the two black curves you see on top. This is the min-max we get out of the testing. So you can clearly see, specifically at the rear, the bandwidth what we got in CIE is tremendously larger than the bandwidth we see in testing. And again, perhaps if you look at the min-max curves here at the rear of the car in the bottom picture, they perfectly run in parallel. Yeah. So what that means is all these wind tunnels create exactly the same airflow along the rear end of the car. That's very obvious, and you can see how that continues. Now you see again same logic, underbody center line. You see the shifted data. I think before you still had the impression data becomes somewhat closer, but I cannot see that that's happening anymore in the underbody. It's shifting. Is it getting closer? I'm not sure. And you see still how tight the band is out of 11 wind tunnels. Very different, very different. Small wind tunnels, very big wind tunnels, but they are still very, very similar. And if you overlay, again, now you have to be careful. Don't try to correlate this because one is open cooling, the other one is closed cooling. So there has to be a difference in the middle section where there's airflow injected from the open cooling case. So we cannot expect that this correlates. It should just indicate this is the bandwidth we see in test. That's the bandwidth you see we see in CIE. That's the last slide. Repeating, we are now looking at the rear end. You see our predictions. You see the shifted predictions. You see the bandwidth. Keep in mind the scaling of the CP axis, and you see the overlay, and you see how CIE obviously shows a much bigger spread. I hope that answers some of the questions many of you had in the past. Yeah, about do I have to include the wind tunnels because they will be all tremendously different, and only if I have this specific wind tunnel model, I will be able to match this. Again, we can continue this discussion for a long time. We discussed this yesterday a bit. That doesn't mean at all that there is no value in modeling the wind tunnel. Yeah, that's a different story, and I don't want to get into that discussion at this stage. So that's not what I'm saying. Yeah, but for the problem we try to solve here, it doesn't matter that much. For the sake of time, let me quickly go to AutoCFD4. So 19 participants submitted 79 results. That's, like Gary said, pretty much similar to what we had last time. There were submissions for all the different TFGs. I should say that I would have hoped for a little bit more submission out of the AI world. Neil already indicated that it was perhaps a little bit too early to start this, but still, I think it's an important thing. It's good that we did it, and I think we should continue doing this. Everybody used the spreadsheets. I got all the data, and as I said, I'll work through this and we'll send you feedback. A little bit of statistics. So as I said, it was pretty much all CFD, just one data set out of the AI. It was this time a big spread in different software tools. Yeah, before we had the traditional big players in the market dominated, but you see there's 50 like others, so all kind of different codes. ANSA measures were still used, but then again, a lot of people tried their own measures. A clear focus on hybrid methods, only a few runs, also after the conclusions we had last time. More LES happening. Pretty much everybody is doing transient, only a few, the run stuff, steady state. The thing which is still a little bit, should I say disappointing? Yeah, but or better to say, we didn't pay enough attention to is the statistical relevance of the results. Yeah, if we look at the mean calc stuff, I would say that the vast majority here shows a red or at least yellow thing. There is just a few where I would say they fulfill all my requirements. Yeah, in terms of what mean calc would say, what should be the right averaging interval. I would say, and that's just my personal setting, I would say if you're not running more than 1.5 seconds, then I think from all the experience I have, your results will not be reliable enough. Yeah. And so I think that's something I would really say we need to pay more attention to. I think the yellow stuff was something where I had the feeling that mean calc has not been correctly applied and numbers were a bit dubious, so something we need to check perhaps. From an overall result perspective, things are not really changing so much. So you see, and that's the next slide, says AutoCFD2 upper right, AutoCFD3, AutoCFD4, AutoCFD3, AutoCFD2. You see the spread is very similar. And if you look at the picture, perhaps you get the impression things are kind of similar in terms of how far they are away from the testing and how big the spread still is. There's a bit of clustering happening. That's out of the noise factor investigation. Yeah, if people do noise factors, then they would obviously not see that much change in drag. That is because we have this clustering sometimes. That's the same for lift, same story. So the spread is very similar to before. You can look at the graphs. Again, I would just repeat myself, so I rather jump to the next ones. Again, that is the upper body centerline pressure. The thing which has changed, as I said before, in AutoCFD4, I shifted the data so that the pressure at the probe 107 is all the same. It's actually the test data I'm using here as a reference, but you can still see that if anything, the spread at the rear of the car, at the rear window, is even larger than what we have seen before. Yeah, that's perhaps there's some new technologies tried out, and that perhaps causes this. So I'm not saying we're getting worse. That's not my message. We are certainly making progress, but there's obviously still a lot of spread. And this is, again, I did the same as I did before. So findings in terms of steady state and transient, that's still the same. Yeah, you see the steady state stuff in the same way differs from the transient, and it also differs from the test, like we have seen before. So that's remains to be consistent, nothing new here. This is perhaps something interesting. I think Charlie suggested this, and I think it still needs to be looked at very carefully. But what this is, this shows I've taken the shifted CP data you provided and has subtracted for each and every probe location the test data. And I used the absolute values of this and calculated the average. So your average delta between the measurement and your predictions for all the probes. And this is what I got. Yeah, so there are, I think the best ones are like here in this range, where we have an average delta of a bit more than 0.02. We obviously have some other cases. There is some correction data. We already talked to the person who submitted this, so that data got corrected. I've just not managed to put it in, so let's not worry about these. But then, yeah, we still see that there are outliers. And let me show you just a few things. It seems to be that's colored by the participant. So I think there seems to be a correlation between the difference you're predicting to who predicted this using his methods. Yeah, so there seems to be, I see this big block or that block. And here there's perhaps a little bit more variability in this, but you get a bit the impression that there is a correlation between who did the work and how much did it differ. This is the perspective on runs, LES, and hybrid methods. You can see that the runs specifically here, the red curves are all seem to stick out a bit. These are different. They seem to be better in this case. You also see that the LES still seem to be a bit further out. There are some pretty good LES stuff, so I'm not saying it's across the board, but there seems to be a bit of a reoccurring theme here. That's like under measures and others. So again, if you ignore those which are incorrect, I think the under measures are still across the board doing pretty well. The other people trying change some stuff. It seems to be a bit more problematic overall. Let me jump this, otherwise I have to stop here. This is just my few last slides regarding the delta of the front wheel deflector. And again, the story remains to be the same. You see the impact for the different, I think I've not properly named this. This is AutoCFD3, and this is the aerodynamic forces. And if you look at AutoCFD4, it is the same story. Yeah? The numbers, the percentage of runs which fulfill my accuracy requirement is pretty much the same. It has not really improved. And you would see the same if you look at, this is AutoCFD3, you see the deltas in terms of pressure. And if you look at AutoCFD4, it's reasonably similar. That's is not a major change. Again, I know this was a very quick run through because time is limited. If you have more questions, feel free to talk to me, and certainly there will be more data, and perhaps we have some more time to talk later throughout the workshop. Thank you.